not actually. Happens. Oh, that's a problem again. Somehow I cannot. Yeah. It is there, but not here. Yeah. A slide rather. Well, this weekend. I mean, no, it is better if we escape and escape. No, let's view. Slideshow. Okay, that's it. Okay, that's great. Thanks a lot. Thanks a lot. Hope it works. So I start like this. No presentation.
It's a pleasure for me to introduce you Professor Povas. He's a famous expert of film model and graph physicists. Let's enjoy.
Okay, thank you. Okay, good morning. It's Monday morning. We're 5 minutes late. So we're inside the academic uh, rules. So I hope you enjoyed the first week of the school, and I'll try to keep on with the standards. Yeah, my idea is to convey to you a global idea of what is nuclear structure physics at low energy, incorporating many of the things that we have learned in the last years, which give us, in a sense, a perspective which is not written in the books. So essentially, we plan to conclude that what is written in the general books, it's not, I would say, not even wrong, as it's said sometimes. It's just marginal, I would say. Maybe because of the real complication of the difficulty of the things, but out of this difficulty associated to the fact that the atomic nucleus is a very complicated system. It's a many-body system with many particles interacting with a very complicated interaction. At the end of the day, I want to give you a bit of a new simplicity, which is completely at another level that the established simplicity, which essentially is very limited, is no practical really interest or theoretical interest. Okay, so I will start, and maybe you all know that, but we have to fix the language and to be sure that what I'm telling you is meaningful. So most of the first hour or half an hour is extremely elementary and aim to fix the vocabulary, in a sense. So this is what I call undergraduate nuclear physics in a nutshell. And once we have fixed that, we can go on. The idea is to give an unified view of nuclear structure. Unified view means essentially that what you have learned as a dual manifestations of the nuclear dynamics, which is single particle language and collective language, will be unified in something. So my aim is to arrive to a description of collectivity. Collectivity is something which is proper to nuclear physics. All the nuclear matter colleagues are very happy saying, well, more is different. And emergency is the key word. And so on, they are so happy. But all these things happen in a really brutal manner in nuclear physics already, in nuclear structure at low energy. And we will see many examples of this, which are of dramatic, this is very dramatic nature. So one of the messages at the end of the day will be that contrary to what is written in the books, the key element in nuclear physics is collectivity, the emergent phenomena, not the single particle degrees of freedom. The single particle degrees of freedoms are there more as a background, as a basis, than as the real physical problem. This will be the aim of the course. And in this sense, is a different view from what is written in most of the books. Well, many of the things, most of them, of the things technically are written in the books, but the story is different. My narrative is different. Okay. So from this undergraduate nuclear physics, I will introduce the interacting shell model as a way to unify everything. Then I will discuss in a not very common way the effective interaction, because finally it will be the effective nuclear interaction that will produce all the physics. It's weird, Hamiltonian driven. So once you know your interaction well, all the manifestations of this interaction will be easier to control and to describe, okay? And with these tools, with this brick, I will go into collectivity. Once you have understood that the effective interaction, which are initially very complex, can be read in a simpler way, and once you can select which are the dominant correlators, the dominant part of the interactions that you have to deal with, then this interaction will be the protagonist of this emergency of collective coherent features of different nature. It could be superfluidity, it will be phonons, it could be permanent deformation of different types and associated rotational features. Okay? So this is the plan. So let's start from the very beginning. What are our starting hypotheses? First, we use nucleons. We don't use quarks or mesons, etc. We will use, it is not always necessary, non-relativistic kinematics. Sometimes you can use relativistic kinematics for working at low energies, but this is not a very fundamental issue. instead of solving a Schrödinger equation, you solve some kind of, at a given moment, you do some Dirac stuff, but it's not a basic issue if you want to describe collectivity, because even if you start with a non-relativistic kinematics, at the end of the day, you want to treat collective phenomena, you come back to things that are very similar to what you do in non-relativistic kinematics. Well, these neutrons and protons are bound by the strong nuclear interaction, which is just the projection of quantum chromodynamics in the space of neutrons and protons. And this, from the very start, is the origin of the complication. It is not that QCD is a very simple theory, because it's strong and low energy. It cannot be, the problem cannot be solved in perturbation theory. And we are still at the stage where describing one single nucleon with QCD, it is a serious problem. You should use non-perturbative methods and do lattice QCD and whatnot. And even so, you cannot really pretend that you understand the proton ab initio, in a sense. So imagine if you go to Lead 208. It is not probably the correct road to proceed. Not for the moment, at least. So as the interaction is a reduction of QCD to the space of the nucleons, you have the usual problems. When you reduce you can have a very simple interaction between elementary constituents, and if you need to change the protagonist of your problem because of having too many, for instance, the price to pay, and this is effective interaction theory, this will happen this will be coming all the time along. The price to pay to have simpler constituents is to complicate the interaction. Imagine atomic physics. We have only the Coulomb potential, which is simple and well known. And you solve your atomic problem. Okay, you can solve it. You can solve the simplest problems, and even the heavy atoms, you can solve the problem. Okay, but when you go to molecules, then you have many electrons in each atom, and even if the interaction is simple, to proceed and treat both all the nuclei which are there in the molecule and all the electron is not the way to proceed. What you do is to project into the space of the coordinates of the nuclei and forget about the electrons. And when you reduce this, when you eliminate all the electrons, etc., and reduce to the coordinates of the two of the atoms, in a sense, you get a new interaction, which is no longer the Coulomb interaction. Typically, in the case of noble gases, you get the van der Waals interaction. In the case of QCD and the nucleons, we're going to deal with a kind of van der Waals nuclear interactions. This is the reduction to the space of the nucleons, of all the complications of QCD. So we should expect complications. And in the case of the nuclear interaction, the complications are extremes in a sense. It is not only that the radial dependence of the interaction is different and more complicated, it is also the fact that all kind of terms, almost every term in the interaction that you can produce without violating the symmetry principles appears in the nuclear interaction that you have to build if you want to reproduce the phase shift and the properties of the nucleon, or of the two-nucleon system, which is the deuteron. And a little bit more with three-body, etc., that I will mention along. So this is a problem. The bare, let's call it bare nuclear interaction, has a very complicated form. Remember that you have a very strong, extremely strong short range of repulsion, followed by an intermediate range attraction, and then a tail which is simple in the sense that can be reproduced with just the fact that you exchange a pion. So our van der Waals interaction will have this kind of shape with an extremely short-range repulsion, and this extremely short-range repulsion is at the heart of many of the problems of nuclear theory. But this is just the radial part. But if you go to other terms of the interaction, you have, as you know, spin terms, spin-orbit terms, and just to bother you even more, a novelty, which is probably a more complicated terms of interaction in physics, which is a tensor term. Tensor term is called like that because essentially it's an interaction in which you have kind of tensor of rank 2 in the normal space. The vector R is a vector, is a tensor of rank 1 in angular momentum. So it behaves as an angular momentum 1. So you can couple an angular momentum 1 and angular momentum 1 to make an angular momentum 2 and an operator of angular momentum 2. And this is a tensor of rank 2 under the rotational group O3. Okay? But you can do the same with the spins, because the spin, you can couple the two spins, which are again vectors in angular momentum, to a rank 2, and then you go back and you make a scalar, because all the Hamiltonian term, as the Hamiltonian is rotationally invariant, have to be scalars. Okay? But this is real complication, you know? This is a very, very extremely complicated thing. If you write this, remember that these are the Pauli matrices. You have to couple two Pauli matrices with Clebsch-Gordan coefficient. You have to couple the Cartan components of a vector. That you have to the vector in the Cartan basis, which is the angular momentum basis, and couple this object to a tensor of rank 2, and then recouple everything. So this is a mess. Okay? So the interaction, this is this point, has a complicated term. And the two complications, the two basic complications are this one, and sometimes this one. The other ones are less dramatic. Well, all these terms are needed to really describe the deuteron. Remember from your undergraduate courses that the need of the tensor force is forced by the fact that the deuteron has a quadruple moment which is different from 0, and the only way to have a quadruple moment different from 0 is to have a tensor term in your basic interaction. And you need everything